Right, so I got an email asking, can I go over the ring opening mechanism for acidic versus basic and would it give different products? And the short answer here is like, this is a good question, but it's also kind of dipping in way too much depth for epoxides. So with epoxides, we're just going to more consider like your basic ring opening mechanisms. But let's say you had an asymmetric epoxide. So we're going to do this one here. So we have a tertiary carbon here and a secondary carbon here with regard to which alcohol would be formed. The question is what happens when you do ring opening for acidic versus basic. So with any ring opening, we're going to have some nucleophile, be it a cation or an anion, attacking this particular alcohol. Now, the challenge here is that we're probably going to generate chiral centers, and the question is the nucleophile on the chiral center, is the oxygen on the chiral center, what chirality do you end up with? And so you can see quickly how these types of problems get very, very, very complicated, even for very trivial and simple examples. When we get done here, we're going to end up with one chiral center because I have two methyl groups. But if I were to do something like, actually we can't make this up, so I have an ethyl group and a methyl group, and the other end I have a hydrogen methyl. So I'm going to end up generating two chiral centers here. And where the alcohol and the nucleophile end up depend on the mechanism for how we open the ring. So this is going to follow a lot of the analogies that we have for ring closing metathesis. So we have the option of an acidic pathway or basic pathway. And I'm just going to write the OH here to mean basic. I don't mean that there's hydroxide present, but the H plus for the acidic conditions, we definitely have the H plus. So our first step here to encourage the opening is to add our H plus to the oxygen, because this is kind of reverse of the mechanism. In fact, if you look at a lot of the mechanisms for ring closing, they're in equilibrium, they're reversible, and because of that, we end up having, I don't want to say this, we end up having basically the reaction go in reverse from what we'd expect for the acidic or basic. So first thing we're going to do is we're going to protonate our oxygen, and then we're going to open it up to a carbocation, and this is where it's going to get dicey. So I guess I should be drawing in some stereochemistry here. So when we open up this oxygen, we've got the hydrogen going back, and we've got hydrogen coming forward and the methyl group going back. And we end up generating our carbocation intermediate. Well, this carbocation intermediate means that we're going to end up with two enantiomers here. But also keep in mind here, we've got this ring rotation going on to the other side. So not only can these, so basically this, whatever your nucleophile is can be added cis, we're going to say cis even though it's incorrectly, cis with regard to the OH, and trans with regards to the OH. So we're going to end up with that version, and we're going to end up with that version. So we're definitely going to have the mixture of R and S here. But for the epoxide, for the oxygen side, we're only going to get one chirality because it doesn't have a choice. It can only open up one way. So this is going to be the same chirality. But whatever our nucleophile attaches, this is going to be a mixture of R and S. So if you go through the acidic pathway, the oxygen that is in the epoxide, that's going to give you an enantiomically pure alcohol. But your nucleophile is going to give you a mixture of both the R and the S. So let's say, just for sake of example, this is an S, we'd end up with the R version. And again, I'm just going to arbitrarily these R and S. I don't know what they are. I'm not going to work it out right now. But we're going to end up with the SR and the SS mixtures in this case, assuming that that OH group is an S conformation. So this is basically your analogy for, and it's an Sn2 mechanism, or Sn1 mechanism. So this will end up going Sn1, and you're going to get a big complicated mixtures of both the R and the S. What happens if you go through the basic? Well, the basic here is going to promote the Sn2 pathway. And typically, our base here is whatever the nucleophile is. And because we're going through a Sn2 pathway, we have to let the nucleophile attack through the least substituted carbon. And so in this case, it's going to attack here. And we're going to end up with OH. See that yet? So your nucleophile ends up anti-periplanar to the OH group. But here we do get an antimerically pure mixture. So let's say this is S and this is R. We're only going to end up with that one S and R conformation. So when it comes to asymmetric epoxide opening, yes, pathway does matter, SN1 versus SN2. That said, we tend to cook our problems so they look something like this. So you don't get these competitions between SN1 and SN2 pathways, and you don't end up with these really complicated R and S mixtures. Now, this is not to, so don't read this to say like, oh, we just do this because it's too complicated. It's more about what you're trying to accomplish at this level. Organic 2 this is something that would be very good in an Organic 3 course. So when I took undergraduate chemistry, one of my degrees is in chemistry. I had Organic 1, Organic 2, and then junior I took Organic 3. And Organic 3, this would be a really good course to go through because at this point you should have gone through epoxide mechanisms. You should be familiar with SN1, SN2. You've got some inorganic under your belt, so you're familiar with group theory. You're a lot more comfortable with this. But I would say this is kind of dipping more towards Organic 3 because at Organic 3 you are probably going to be a chemist. And so it's important that you really fundamentally understand these mechanisms and actually honestly be able to derive this yourself. Kind of like figure it out, maybe a little bit of help from the structure, but kind of get to this idea that, okay, acidic and basic really matters because acidic and basic is going to dictate whether this is effectively an SN1 or an SN2 and what I expect to see with this. I think particularly for Organic 2, you start missing the big picture when you start focusing on these details first. So for Organic 2, my ethos is that understand that there are ring opening and ring closing mechanisms. The ring closing, you have the SN1 and SN2 pathways, what they look like, because the alcohol is acting like a nucleophile and pushing the other one out. But as far as generating epoxides, this is kind of more like a big picture, like, oh, this is how epoxides are made. If you go on for a higher level course, you can talk about epoxide opening mechanisms depending on the flavor that your instructor is interested in. But if you want the full story, like this is what happens. And it's back to SN1 and SN2, which are Organic 1, Organic 2. But I think particularly at the Organic 2 level, this is a level of rigor that's too much. In principle, I could assess you on it, but I think this is more relevant to a junior level or senior level Organic 3 course. Because at that point, you're probably going to go off and be a chemist and actually use your Bachelor of Science in Chemistry in your future degree. So you need to be able to understand how acid and base change the mechanism and how that mechanism changes your final answer. But for Organic 2 kind of being a pathway for chemistry majors, we cover epoxide, but being a pathway for nursing majors, PA school, med school, PhD programs, chemical engineering programs, this is a little too in-depth. This is a little too much chemistry focused and less about the big picture. So hopefully that addressed the email I got about this. Again, like, it's a good question. Like, I'm not disparaging the person that asked this. Like, this is a very good question. But I think at our level, it's a little too high level. You shouldn't be so worried about this depth because this is actually kind of more like a junior level organic chemistry course where you're given like, here's a 3 carbon molecule. Now take it and make it a 25 carbon molecule and write all the synthesis steps out along the way. By that point, you should be pretty comfortable with, on your own, dissecting whether it's an SN1 or SN2 pathway. All right, so I've got the chat menu open in case anybody has any questions. I'm doing a little bit of work this morning. I'm trying to figure out the best way to represent a reaction. So if you got questions, type them up in the chat. Actually, make sure there aren't any up in the chat right now. Oh, we're good. And again, these are not lessons, these are not lectures, these are office hours. So if you have questions, please feel free to ask them or email in advance. Otherwise, I'm here working on course improvements. So just got a question for the oxidation. You use stepwise process how the hydrogens are removed and which are removed in order to form an aldehyde carboxylic acid. I will not go through that mechanism. 2 reasons. It is way too high level for this. 2, the mechanism in the book is wrong. So you're dealing with transition metal chemistry. Organic chemistry is going to focus on transition metal, Lewis theory. Transition metals do not obey Lewis theory, and so any approximation you write of the mechanism based on that is just going to be straight up incorrect. So more you need to focus on the big picture of what goes on with the oxidation, because again, I can give you a mechanism and you can go look up the mechanism of chromic acid oxidation. You will find that what is written in organic textbooks differs a lot from what's written in inorganic chemistry textbooks. The inorganic chemistry textbook is correct because the inorganic chemistry textbook is using molecular orbital theory, which is the correct way to describe transition metals. Your textbook is going to use Lewis theory explanations, and those are not correct for transition metals because transition metals use they violate 2 massive assumptions of Lewis theory. 1, they use d orbitals, and 2, they do through bond. Particularly anything involving a transition metal is most likely not correctly described by Lewis theory. Worry about it when you take an inorganic chemistry course that actually goes to the theory on how to explain it. So a great example of this is the Vedic pathway. Part of my graduate research was looking at the Pseudo Vedic pathway because we've talked about, or we are going to talk about Vedic reagents if they aren't covered in this unit already. I think they're covered in the next unit for aldehydes and ketones. It is a similar pathway for transition metals, but what happens with transition metals is they do what's called the Pseudo Vedic pathway, and with the Pseudo Vedic pathway, you form a square intermediate with a transition metal in the center. None of that is explained by Lewis theory. That's a lot of through atom bonding, which can occur in Lewis theory. So the bigger thing we focus on with oxidation of alcohols is we want to see how many hydrogens we have available for removal. So the first thing we do when we oxidize an alcohol is we form a double bond to the adjacent oxygen. So this would be the first oxidation. The second step is we add an alcohol. It'll look like an alcohol, so this is going to be a carboxylic acid. The last and final step we do is we form another double bond. So I've written this up here strangely for a reason. So if we just have so let's focus first on tertiary alcohol. So with the tertiary alcohol, H here, N is 0. So you can't have N-1, which means these can't be oxidized. There's no hydrogen on the carbon to be removed for the oxidation. Because what we're doing by oxidizing is we're tweezing off a hydrogen and replacing it with an carbon-oxygen bond. For secondary alcohols, we have 1 hydrogen, so we get to this point. So we do the N-1, which will give us 0 hydrogens, and this gives us the ketone. If we have another hydrogen, so in this case N equals 2, we have 1 more hydrogen to get rid of, and so we end up with an alcohol. Now let's say you start with something like methanol with 3 oxygens. There are 2 ways people write this reaction. 2 ways I've seen it written. One is that we ditch, so let's say this is another hydrogen. One is that we get rid of this hydrogen and we make this dicarbox. It's a weird specialized compound. It can be isolated. It does exist. Most likely, though, you're not going to find like anything capable of doing. Like this is a very specialized reaction. Another option here is to take this hydrogen that was here. So in this case, you've got formic acid. I think this is formic acid. 1 more oxidation would actually take you to CO2. So yes, if you had like something like Jones reagents here and there, you might be able to convert this to an alcohol. But far more likely what you're going to do is form another carbon-oxygen double bond, because that's what you did to start with, and this will get you CO2. So those are all the different levels of oxidizing an alcohol. If you have a tertiary, there's no hydrogens to be removed, so it doesn't do anything. If you have a secondary, you can remove 1 hydrogen, so N-1 here will give you 0. You end up with a ketone. If you had a primary alcohol, you have 3 hydrogens to get rid of, you'd form the double bond here, OH here to give you the carboxylic acid. And then if you had 3 hydrogens to get rid of, like with methanol, in principle you could form this dicarboxylic acid with a single carbon, or more than likely what you're just going to form is the CO2. And the reason I say that, when we talk about ketones, this is actually you should recognize this. Oh, yes, that is formic acid. No, it's the carboxylic acid. So this is actually an equilibrium. With this. So if you take CO2 and you dissolve it in water, it actually acidifies the water. The reason being is we get nucleophilic attack of the carbon. And there is an exchange mechanism with the water that swaps these hydrogens out. So you get carbonic acid. Not formic acid, it's carbonic acid that forms. And carbonic acid is formed when CO2 reacts with water. So actually any complete oxidation of methanol is just going to give you carbon dioxide. And if you have water present, yes, you'll end up with this acid. But this is carbonic acid. And this is what makes sodas acidic. But again, as far as the mechanism goes, like there is one in the book, I highly disagree with it. But transition metal chemistry is not as straightforward as Lewis theory tries to make it look. So the reaction I worked with was this. And so if you add ethylene, the first step here is that we form, what was this nightmare compound? This will eventually form the R here is rhenium, a square planar complex. So let's put a red carbon in there to make it a little bit clearer to see. And the way you draw this mechanism, this carbon attacks this carbon, which breaks the double bond, which binds to the rhenium, and then we get decomposition. So with decomposition, this bond kicks up, this bond kicks down, and we end up recovering this. So this is kind of a weird, this is what's considered the pseudo-Vedic pathway. Vedic reagents act in a very similar fashion with the phosphorus carbon double bond, and instead of having rhenium we have a phosphorus here. But the true mechanics of what's going on here, you have oxygens above and below the rhenium, the OH group pointing out, and you actually end up with a trigonal bipyramidal molecule. When you're done, this molecule uses the D bonds to make this happen. In fact, this initial bond breaking here is due to electron withdrawal from the rhenium. So what happens is the double bonds in that double bond in ethylene actually bonds to the rhenium d orbitals, which don't have any electrons, loses the electron density, which begins to break the carbon-carbon double bonds. So we have transfer of electrons from the bonding orbitals on ethylene into the vacant d orbitals on rhenium. And this is what initially forms the carbon-carbon bonds of rhenium. And then because they're sharing electrons to the d bonds, they basically stop sharing electrons through rhenium and they pass it to each other, and then you get the decomposition back into the starting molecule. You can research this for a long time. So that's the mechanism, and this is actually an incredibly simple pseudo-Vedic pathway. Something like chromic acid is a lot more complicated because now you're having to explain how Carbon is connecting to, because right now, really, we don't have too much electron transfer. Technically, rhenium is changing its oxidation states here. It's going between +7 and +5. That's a formalism, but you can kind of get away without not really having to consider the oxidation states in this. When you're changing the oxidation states of your transition metals, it gets a lot more complicated, because where you're putting electrons in the molecule dictates where how many bonding and anti-bonding electrons you have. And actually, this is why you see that color change with Jones reagent. It goes from orange to green, is because you're changing the filling of the electrons in the d orbitals. So I know that's a lot, and it's meant to illustrate a point, is that with transition metals, it's not as simple as it looks for the organic molecule. So in Sn1, Sn2 pathway, you're generally only drawing one electron transfer step at a time. So for like Sn2 or Sn1, at most you see 1 or 2 arrows. Here you're seeing at least 2 arrows with every step, because we're having to describe how the electrons are moving through a whole bunch of d bonds to make this happen. And even then, this is an oversimplified picture. One of the best classes I took in graduate school was a graduate or inorganic chemistry course. And we worked with a hypothetical model which was this. We had a metal drawn like this. So we have ethylene giving its electrons to the metal. And the way this is happening is that if you draw the ethylene, you've got your sigma bond, and then above and below, you've got your pi bond, and then the metal has its d orbitals. And so these form bonds with the pi system. So if you look at the energy of the pi, versus the d orbitals, if we start with a low pi bond and a high d orbital, what'll end up happening is we don't get any electron transfer. And so this bond here, this looks very much like, so this would be a situation where we have what we'd expect is a metal with a coordination bond to the double bond. Now if we flip the scenario, let's say we have the p orbital being high energy relative to the d orbital. What will end up happening is that we lose electron density to that d orbital. And so the way this looks is that we actually end up breaking the carbon-carbon double bond and forming carbon-metal bonds in its place. So this is the two extremes with alkene bonding to transition metals. One is a very loose bond where what's really kind of holding them together are charge differences. There is a bond being formed, but it's not a particularly strong bond. To the other extreme, where the metal has actually taken electron density away from that double bond and formed a carbon-carbon bond, in addition to the bond that was forming down here. So we actually have effectively a double bond back to the metal. We have the initial p bond to the sigma bond, so we have p, metal p plus sigma, and for particularly strong bonding we have the metal d plus the pi. So yeah, hopefully that clarified why we don't go into those mechanisms. But this is the bigger picture. So with epoxides, I would say look at the example and determine if you're generating chiral centers, and if you are, that's when you need to worry about what forms you get. The other thing to keep in mind with this is whether or not you're even being asked to identify the stereochemistry and whether or not you're being asked to name the compound. So if you're being told just draw the product but don't worry about stereochemistry, there's no point in fretting over the nuances of the mechanism because you're not being asked for it. Naming is a great example of this. You're not being asked to name it. You may be generating a whole bunch of stuff, but it's not being requested of you. So I would say more focus on big picture, what's going on. We're also going to try to cook our examples, so this way we're not going to have to focus too much on chiral centers. So particularly if you look at like linear molecules, symmetric linear molecules. So something like this, if I open it up with acid or open it up with hydroxide, it doesn't matter because in both cases I'm generating a symmetric diol with rotational symmetry. So there's no way here to generate a chiral center because it looks the same both ways. So yeah, we tend to cook our examples here to ensure that, I mean, again, if you're going on for an actual chemistry degree, yes, keep in mind you do need to worry about this at higher levels. At this level, we're focusing more on big picture. What are you making with these reactions, and like where do things end up? We're not trying to do synthetic chemistry at a level that an organic 3 student would be worried about. So synthesizing thing like riboflavin from scratch, yes, that's a lot of chiral centers, and there is a lot of fretting over what mechanism will generate what outcome. We're not so worried about that here because you can lose the forest and the trees very easily with this type of chemistry. You're also going to, because I've said this, so I said at the start of the semester, I think Organic 2 is easier than Organic 1 because Organic 2 does inherently have this limitation that very simple problems can get very complicated very fast just by adding like a methyl group. You saw this with the kinetic versus thermodynamic products. That simply throwing a methyl group in there, creating an asymmetry in the molecule, now creates 4 products, whereas before you just had like 2. And it seems really innocuous. You just added a methyl group. What's that going to do? It radically changes your answer. This is something I experienced when I did graduate math courses, was that you'd have the instructor, oh, I just put a negative in there. Okay, well, this took it from like a simple function to a very complicated, obscure Russian function that was discovered in the 1970s. So it's not, you just can't make these little changes without considering it. The same thing's true here, is that we kind of have to stick to simple examples because we can quickly creep up on super complicated, intricate examples that are super hard to describe even for people who do it. So again, we're going to kind of limit ourselves here, and this is what I think makes Organic 2 easier, is that we do inherently have to limit ourselves so we can focus on the big picture. If you really want to focus on little picture, I'd recommend go for your chemistry degree. In Organic 3, you will definitely focus on little minutiae like this, where, okay, you want to generate the RS form in high yields. How do you go about this in such a way that you pretty much guarantee that you're going to get this in nantimerically pure form? Okay, how does the synthesis change if instead of RS, we want to do RR? Or we want to do SS? Like, how do we modify the synthesis? And this is when you start getting down these rabbit holes of like, well, we can go through an epoxide intermediate. We can do this. We can do this. We can do this. And there's a reason why you pay synthetic chemists what you do. It's because they have to figure these types of things out. Our next question is PCC, PDC, and chromic acid, are they suitable for linear cyclic molecules as well? Yes. The only thing you have to be careful about is when you're working with benzene rings. So I think I definitely know permanganate will oxidize off an alkyl group, even if it's just an alcohol. So you do have to kind of be careful with that. Actually, no, it doesn't do that. If it has an alcohol, it'll reduce it down to a ketone. But if you have branches on the benzene ring, yeah, you have the potential for oxidizing off alkene groups. But generally speaking, it's going to look the same between branched and linear alkenes. Tend to be why we keep the functional groups limited in terms of the molecules, so we can focus on those. Excuse me. But yeah, if it does it for linear alkane or branched alkane, it'll do it for a ring. The big thing with rings, you're pretty much only going to generate ketones if they react at all, because inherently with a ring, every carbon is secondary. Unless it has a branch, in which case it's a tertiary and doesn't react with these things at all. They're also kind of nice because we worry about the PDC and PCC because we have like terminal alcohols, and we don't want to convert them to like carboxylic acid, so we need this gentle oxidation to kind of get us there. What your book really doesn't discuss, PDC and PCC are super toxic. They're nasty, and that's why we don't work with them in the lab. And so it looks great to say like, oh, you should do the PDC and PCC. One lab we're actually developing is a fetazone oxidation. That's silver nitrate. And so you can hold that in your hands just fine, heat it up, and you can get the primary alcohol, you can get the aldehyde. But, I mean, if you're going to work with something toxic, you might as well work with something that's not halogenated, and that's your Jones reagent. So the nice thing about rings is that we can get ketones just through using a Jones reagent. We don't have to go through these super nasty chlorinated chromium complexes. Theoretical yield. So the freezing point, it's not a theoretical yield, it's the theoretical mass. And the theoretical mass is 152 AMU. So 152 AMU, it's vanillin. So if you want to look it up, vanillin, that's why the lab smelled like vanilla this week, is that we were working with vanillin extract. We actually used to work with paradichlorobenzene, PDC. PDC smells like mothballs, and I'm so glad we phased that out. But for this lab, we've worked with vanillin. If you talk to other lab sections, we also have a version of this lab that works with stearic acid. I don't think South Campus worked with stearic acid this semester. But if you're talking to people like, oh, well, no, we work with stearic acid, I think North Campus had the option. South Campus does too. But we focused on vanillin, but definitely in the past we've used stearic acid and PDC. Page 23. Need to get back down to my desktop. Functions is both. So water is going to do both parts of this mechanism. So we've got the, what do you call it? Yeah, originally worked with PDC, and I hated working with that stuff. It just smelled awful. Felt like you were like, I associate mothballs with like elderly relatives, so I felt like it was like visiting my relatives back when I was like 5. So for this example, your first step with the carboxylic peroxy acid is this, and then your water is going to attach to both. And we're not going to worry too much for the stereochemistry here. Under neutral conditions, you're right, it's going to be kind of splitting hairs, but I think the key doesn't even bother with stereochemistry here. So definitely this is going to be consistent. This, if you have to do it under neutral conditions, I would treat it like it's base. Well, actually, so water has a high dielectric constant, so I would treat it like acidic conditions. So you're going to get a mixture of both the R and the S on this alcohol, because at the end of the day, it's an Sn2 pathway because the water has a high dielectric constant. Page 24, last problem. You're under basic conditions. This is definitely an Sn2 pathway. Oh, ha ha ha. I like that problem. So you can end up with either the cis or the trans. It's hard to get this exact stereochemistry. So we work under basic conditions, so that puts So that's your first step back, is this one. So the oxygen and the bromine have to be antiperiplanar. And the only way to get that is if these two groups are cis. And then the epoxide is done to the same side. So that's how you end up with that. So that's, you definitely couldn't do it you could definitely reverse engineer this, but like how you would forward engineer this would be a nightmare. But yeah, that's why the bromine and the OH groups are drawn on opposite sides. What will happen is that this bromine is going to curl around and push the bromine out. And you end up with basically the oxygen pointing at you. That makes the two methyl group cis and the ethyl group trans cis with the hydrogen. OH is added to both because you're basically, this is just ring opening of epoxides. New graph our post lab. Yes, you need to put your graphs in your post lab, but you can plot all 6 plots on the same graph to save yourself time. So I saw what you did in lab. You do need the graphs for post lab, but you don't need like 6 plots with the 6 rectangles on them. So we can write any epoxide reaction as H nucleophile. In this case, our H is going to open up our ring. And then we've got our nucleophilic attack, which will give us this complex. But in this case, our nucleophile here is the OH minus. So water is being added to this epoxide, and it's just opening it up. This is the reverse of if you took sodium hydroxide. So let's say you had an OH here. And you took sodium hydroxide and reversed the reaction. When you reversed it, you get H2O from the hydroxide and this this epoxide. But it's just reversing diols. So the sodium hydroxide here is just serving as basic conditions to ensure that you're getting the Sn2 pathway. The bromine is the actual nucleophile. Now, if you thought, well, would I end up with a mixture of diols? Yeah, probably. Hydroxide was probably not, sodium hydroxide probably wasn't the best choice. You probably work with something like ammonia, NH3 to keep it basic. But it's also relative amounts. Like we can have like 0.1 molar sodium hydroxide and 1 molar sodium bromide, and this is going to really drive it towards the bromination and not the hydration, not to the diol. But yeah, you would probably, in this case, you would probably want to specify that the sodium bromide is the larger reagent, and that the sodium hydroxide here is just to drive it more towards the Sn2 pathway. So yeah, the hydroxide here is just to ensure that it's under basic conditions and ensure that you kind of get this desired stereochemistry. The sodium bromide here is being run in large excess. Oh man, some cool reactions on the next page. All my early drawings before I started drawing it all in KimSketch. You're welcome. So CH3OH is a neutral molecule, so you can't add a neutral molecule to a neutral molecule, particularly with the leaving group. So that would be my suspicion. I don't have the notes in front of me. Come on. Nope, nope, right there. So the reason you don't add the OH is that that's a neutral molecule. Because the thing is that when you open this molecule, you do add the OH technically, but we'll just consider the mechanism on the right. When you first add that alcohol, when you break the ring, you end up producing a zwitterion. So you end up with the positive charge here and the negative charge here. And then whatever else is in the solution, either the other methanol or the HCl or something, is going to shuttle this hydrogen off into the alcohol. So you do technically add the full CH3OH. It's just that you add the CH3O here, and then the H gets added up here. It is kind of a devil in the details situation where you can definitely like conceive of scenarios where like, well, really it's added from the HCl or the water or the hydroxide. Big picture is that you're going to probably add that CH3OH gets broken up into two groups. One is the nucleophilic part, that's CH3OH minus, and then we need the H plus to finish off the alcohol. Oxidation state of a ketone is actually +2. Yeah, because the carbons don't contribute anything. It loses 2 electrons to the oxygen. So carbon in any ketone is a +2. Assuming, yeah, carbon in any ketone is a +2 oxidation state. So if we look at oxidation states, we have carbon, oxygen. Carbon's going to start with 4 electrons. It's going to get 1 electron back from this bond, 1 electron back from this bond, and 0 from these two. So it puts carbon in a +2. Slide 54. Sulfides. I hate these. It's thiochemistry. What questions do you have about it? Not a huge fan of thiochemistry. And definitely this is a, particularly with a peroxide, that is going to be a finicky reaction. Oxidation of thiols meaning O to S, not adjacent to carbon. So oxidation just means that you're changing the oxidation state. And the traditional meaning of it came from oxidation as you expose a metal to oxygen and it takes up the oxygen, and this does cause the metal to lose its electrons. Same thing is going to be true here. Oxygen is the most electronegative element on the periodic table. So if we're adding oxygen bonds to sulfur, we're inherently oxidizing it. We're making it get a more positive oxidation state. So there are two ways to do this discussed on the slide. Iodate's the most controllable, or periiodate's the most controllable. So you take sodium periodate and reduce it down to iodate, and this will selectively give you a sulfur oxygen. The way it's written there is a formal charge of the plus and a negative. This has to do with the fact that I don't know why sulfur wouldn't want to do that. But short story is you end up with kind of like this oxygen on a sulfur. And then if you want to get the two oxygens added to the sulfur, so you want to get rid of both lone pairs and put sulfur and basically generate, there's two ways to write these. I went off what the book said. Probably an easier way to see it. Let's say you have this complex. The first oxidation here, you have two lone pairs, would be to do this. And then the second oxidation is to do this. If you are so interested in doing that type of chemistry, you can. Sulfides are covered as part of this unit. That said, Francis Carey doesn't go that much into sulfide chemistry or even thiochemistry. And this was most of what I tweezed out of the book was these two reactions. This is guaranteed to be selective if you use the sodium periodate. This is guaranteed if you use a high excess of hydrogen peroxide, but this is kind of esoteric. Most labs have this on hand, so if you just want to do this reaction, you can, but you have to limit it kinetically. Pretty much, yeah. That's how you're oxidizing it. That's how you oxidize carbon. Is you add oxygen carbon bonds. Same thing true of the sulfur. We're just adding oxygen sulfur bonds. Sulfur is unique in this case because it starts out. This is a valid Lewis structure. The reason it's being drawn like this by your book, this is why they're doing it. I doubt sulfur is really looking like this. But they're drawing it like this so sulfur still satisfies the octet rule. Most likely what's really happening is that you're getting sub-double bonding down to reduce these formal charges. Sulfur is big enough to undergo these. But basically, the advantage of putting these oxygens on here, they are potentially acidic, or they can basically create a weaker sulfuric acid. Or they can basically, by adding these oxygens to sulfur, practically you can create an acidic sulfur site. But that's all we're doing with these three examples here is just adding oxygen to sulfur. So sulfur chemistry, it's probably one of those things down the road I'll expand it a bit more. It hasn't been a high priority for me to expand the sulfur chemistry parts of these units. But again, this is all I saw in Francis Carey regarding sulfur chemistry. You're welcome. All right, so that's the end of all live streams. If you ever have questions, please feel free to email in advance. And otherwise, I will see a lot of you tomorrow.